Yeah. So you should be live. Okay. Is there a screen? Huh? Is there a face cam? No, it's just you on the pod. All right. So is it? It's live. Okay. So hello. So welcome to Berkeley Hyperloops' first design review webcast. And today we want to show you what we've worked on. And yeah, let's get started. So my name is Ray, and I lead the chassis subteam. And over the past 2 weeks, we've been converting our files from SolidWorks to Fusion 360, and this is what we have to show. So to get started, first, our chassis is designed with a two-wall system where we have a layer of inner panels and a layer of outer panels, and this allows us to guarantee that we won't have any pressure breaches or any thermal flux through the system. We've catted this and colored them here red and blue just to distinguish. That aside, we have recently changed up some of our internal walls structures to actually have beams that are supported and welded to the rest of the chassis. This both provides structural rigidity to the wall as well as strengthening the chassis. Also, the aero profile has been slimmed down and extended, and this was both to give us less drag and to also allow us to fit our air tanks. So, yeah. Neil, yes, you.
Hi everyone, my name is Neil. I lead the internal systems team. So just a brief overview of what we do. We focus on the levitation of the pod as our main component, and we also get the lateral stabilization down. So main thing we're working on right now is our air bearings. So this thing I'm loading right here. Okay, so yeah, this is our current air bearing design. We're still prototyping with them to find out the complete perfect model, but as of now we have structural backing under which we have porous layers, and we're doing one more porous layer and one less porous layer so we can get the airflow to be as laminar as possible. And ideally we're trying to levitate about 3 millimeters. So in order to calculate how much air we need going in, we actually looked at the New Way paper, and based on our weight and the surface area we have, we can find the input pressure, and from that we can find our required mass flow. So where do we get the air from? The air comes from our air tanks, which are in an array like this. So we've been looking at Faber air tanks because they provide the optimal amount of pressure and hold enough mass. So they'll be in an array like this where 5 air tanks join to form one nozzle, and then these will be branched off in the front and in the back respectively in order to go to not only the vertical air bearings but also to the lateral air bearings. A quick note on the lateral air bearings, these go along the I-beam and are, so as you can see right here, these are from OVCO, who we're still talking with right now, but these go along the I-beam. We have 2 on each side in the front and 2 on each side in the back. And these make sure we're stable in terms of the yaw direction. So if there is, if we move closer to the I-beam on one side, the force from this will auto-correct it, and same thing on the other side. So yeah.
So people watching through the webcast, yes, we can actually see the questions, and we will be reading them out and answering. So questions about this. There was a question from Ben H about system diagram, system design. So Mitch.
Okay, one sec. I'll quickly flip over from our screen share of the pod. Oh, and I am live. Hello. And go into this guy. So pretty much our system is set around a canvas, and this is pretty much the networking protocol that we're using to talk between our different computer systems. This part.
Yeah.
Keep going. Okay, we're good. So pretty much the canvas is the central nervous system of everything. It talks between all of our different computer systems, set priority for different tasks, and make sure that all of the communications reaches the destined computer on time and in the right order, so we don't have any data conflicts or any of that kind of nature. I'll start with down at the bottom with our levitation gauge. This depicted one system is actually going to be split into two computers, or two embedded systems. One that will directly control our air bearings and make sure that we are flying at the right height for the entire duration. And another that will be in direct control of the air brake and the eddy current brake. This is to add redundancy and just allow us to better control how we are braking the pod versus how we are flying, and to make sure that those two systems, which are very critical to the actual success of the pod, aren't dependent on each other. Moving over to the air tanks and batteries is kind of the next logical step, since the air bearings directly rely on this, and we need to make sure that the pressure in this system is at the correct level at all times. Otherwise, we will drop below our minimum of 3 millimeters, and this will cause us to potentially scrape against the track. So additionally, if we go over to our interior computer, this one is responsible for monitoring at all times the interior of the pod and make sure that the passengers are safe. This will be somewhat separated from the rest, since its primary function is to deal with passenger emergencies and to deal with the cabin and stabilization and make sure that the pressures are all the same and the air compositions are good within the cabin. So it won't be directly interacting with any of the outside systems besides the communications over here. And it just relays that everything's fine, that there's no emergencies with the people inside. Moving on to navigation and the communications, these two computer systems kind of go hand in hand. So navigation tells us where we are in the pod and how fast we're going and all that kind of good stuff that we need to know at all times. And communications is the real key one, where it relays all this information out in packets and sends it to us on the command side. This is obviously done through the SpaceX network controller. And that's about it for the system. Okay, so we're going back to Neil.
Hi, so I noticed that some of you had some questions for me, so yeah. Okay. I noticed that some of you had questions for me, so I'm going to go through them and answer them real quick. Let's start with, okay, so first question is, how confident are you with their air bearings providing lateral stability? So these air bearings are from a company that manufactures lateral air bearings, and once again, we are continuing to talk with them, so they will work with us to get something that fits our specifications. But these have been industry verified, and they have ratings for gaps. So based on that, and based on some testing and prototyping we're going to be doing later, we'll be able to calibrate them properly. Okay. Next question. How many tanks would you need for your entire run, and would the size be unreasonable once you run a 255-mile tank run? So yes, so for this competition, what? Oh yeah, sorry. Yeah, in case you want to see the tanks again. Yeah, so for this competition, we calculated so far from the New Wave paper how they calculated their required masses of how much air we'd need. So I took that amount of air and I scaled that up to provide a factor of safety for how long we can levitate. And based on that is where I got the 10 air tanks. And these can be filled to our desire. We're looking to do at least 100 pounds, but that's going to change based on our testing and what we get and how we scale. Okay, so what is the gap for your lateral air bearings? So as of now, we're doing slightly over 1 millimeter. So these, I know these air tanks are rated for lower than this. The air bearings are rated for lower than this, but the idea with these air bearings is that they're constantly running. So in the case that you do get near the I-beam, the air bearings will auto-correct themselves and will stabilize the pod. One sec. So okay, final question from me. It looks like I noticed. I'd like to ask you about how you're approaching your air bearing designs. You mentioned porous membranes and New Way. Yes, so we in our research we referenced the New Way paper on air bearings, where they did calculations for required pressure, and based on that, we're looking into both square designs and circular designs, and after that, we're prototyping them with smaller models, and then slowly scaling up and seeing how these models scale as a whole. And from that, we'll be able to generate our final design. Let me see if there's anything else for me. Okay, so it looks like there's one more question. Okay, so ride heights versus load. Yes, we will be doing, as of now, our calculations are theoretical. We've been writing MATLAB scripts for them and inputting our values and seeing the kinds of results we get from that. After these are done and we've talked with these companies, this company will personally manufacture some of these air bearings and we'll test them. And based on that scalability, we'll be able to judge how this is going to play out in a larger scale. Yeah.
All right. So, hello everyone. I'm Tyler. I'm the lead or one of the two co-leads of the acceleration and braking sub-team. And so I'll just be talking a little bit about our approach for our braking during this, and then when I finish, we can go over these other questions that people are asking. So basically our brake design, unfortunately, I don't exactly have the full PowerPoint up on this computer, but the design of our brakes, we're doing a two-stage redundant braking system. So the first stage being an electromagnetic eddy current brake, and the second stage being an air-powered friction brake. So what this does is it allows us to use a non-contact system for the first braking system, which is going to be used from 200 miles per hour down to 30 miles per hour. And so basically what this means is that we don't have any risk of actually impacting the sides of the I-beam at any high speed. So that's definitely going to kind of increase stability in our pod overall. And the second stage is used partially for our slower descent from 30 down to 0 miles per hour, but it's also used as an emergency brake. So in the case of eddy current failure, those friction brakes are going to be able to power the pod or to slow the pod down from 200 all the way down to 0. And there's a factor of safety of 2 on that as well. So we've done calculations on the heat generated in the I-beam due to both of these systems. The very maximum heat that's going to be generated in the maximum temperature that's going to be reached in any one section of the I-beam was calculated to be, let's see, sorry, pulling up the numbers right now. Oh, sorry, the maximum increase in temperature is calculated to be 150 degrees Celsius. So that's within the limits of our brake pads and the eddy current brakes. And we've calculated that is going to be a safe temperature, especially considering the fact that that's only in the very last section of the I-beam as we're braking. Another thing, since we've last talked about our design, we've changed up our base package. Whereas before we had multiple suspension systems for our wheels and for our spacing on the word, our air bearings. Now we've combined them all into one solid base package. Basically, it's going to be a system of welded rods that are going to provide support. Basically, a solid support that all of our components on the base package are going to be bolted directly to, and that base is going to be suspended from the chassis. So this way, everything is moving in tandem, and there's less risk of components getting misaligned and having any issues down at the bottom of the pod there. So here we go. How do you brake in the event of a battery or cam failure? All right, great question, Eric. That is one of the things that we've really identified as being super important to our design. So what we've done actually, the reason that we've made our friction brake spec to slow us down from 200 all the way down to 0 is exactly because of that reason. So what we're doing is we've set it up so that from our air tanks to our friction brakes, since they are air powered, we're going to have a default open valve so that in the event of a battery failure, that valve is going to switch open, and the air is going to be flooded directly into our air chambers, which are going to push our friction brakes into the rail and slow us down from 200 down to 0. So even without power, yes, we can slow down. All right, cool. That's it from the acceleration and braking side. Feel free to ask any questions, and I think we can move on to, let's see, it looks like we've got another question for spring dampening. How do you size the spring and dampening? Friction pad material, that one I can answer. For friction pad material, there's we'll be using a material that's been used in race cars with aluminum pads, which is going to, or sorry, with aluminum what's the word? I don't know, spinning thing that you brake on, which is going to be either a Kevlar pad or a Polymatrix Q compound brake pad. So these are the two possibilities. Both are worth looking into, and we're going to be doing some more testing on that in the future. All right, pod weight. Here, leaving this to Ray.
So there was a question early on about our gross pod weight, and we are following SpaceX's general advice outlined after design weekend, and are planning to keep our pod weight at exactly 2,200 pounds. And regarding how that affects our 3 millimeter flight gap, Neil, do you want to talk about the analytics of the flight gap?
Right. So I believe there's a little bit of confusion about how we're approaching this. So yes, right now we're doing analytic analysis on this. We're looking at a bunch of papers on air bearings, and we've already read through the New Wave paper. And from that, we looked at how they calculated the air gap levitation versus the pressure. And this pressure comes from the weight of the pod. So based on the required pressure needed for that specific levitation height for our specific weight is how we calculate the mass flow. And regulating the mass flow is how we regulate the air gap as well. So I hope that answers the question with that. 1 second.
Okay. Oh, so Tyler, I think there's a question to you. Let's try to read it.
Let's see. All right. Looks like the question is on brake pads again. Usually, so are you braking directly on the rail, or are you braking using wheels and brake discs on the rail? So we will be directly braking on the rail. And yes, I see rotors are anodized hardened aluminum. We are looking into more of these brake pads. We've got a couple options. Either the Kevlar Organics are another one that we can look into in case these ones don't end up working out. We were recommended these by our SpaceX advisors, so we've just started looking into these just a couple days ago. But yeah, we'll definitely in our upcoming design reviews have a settled brake pad and calculations on how that's going to affect the I-beam. All right, let's see which questions are coming up. So, all right, question about the New Wave paper, passing it off to Neil.
Right, okay, so yes, I have mentioned this New Wave paper. I can give you the exact paper. It's called the 20th, and it's called the analysis on pressurized porous air bearings. Yeah, I'll actually just paste the link in the description to prevent any confusion. Okay. Okay. That will be posted shortly. And yes, we have been now as to how we'll manufacture it, and they're going to help us out with that. And I see there's another question about that. So yes, we have a system to see how high we are above the ground, and based on that we can regulate our mass flow, and that's how we maintain the uniform air gap. So yes, it's essentially the mass flow is what changes the air gap. Increasing it increases the mass air gap, and decreasing mass flow decreases the air gap.
So I would like to say this moment, just ask all of our professors and advisors who are present here, hello, and thank you for coming. And do you guys have any questions for us?
The I-beam track is steel.
It is aluminum.
Oh, the I-beam is aluminum. Oh, okay. All right. So in that heat that you calculated, is that all the way from 700 to 0 or?
No, so this is, this right now, we're talking, all the numbers we cited are in terms of competition. So competition maximum speed is going to be 200 miles per hour. And then another thing also is that the number that I cited, the 150 degrees Celsius increase, that's not over the entire aluminum I-beam. So that's the maximum increase in temperature we're going to get. Because basically, as we're going along, we're going to be going along a huge stretch of I-beam per second, right? And at top speed, the increase in temperature of the I-beam is actually negligible because we're moving so fast across it. But as we get down to lower speeds and we're spending more per section of rail, that's when that 150 degrees Celsius point hits.
At the maximum?
At the minimum, like as our speed is actually, it'll actually be in the kind of, I think it's the 15 mile per hour down to 0. If we're decelerating at 1G, that's going to be where we're going to hit our top temperature in the rail.
In the rail.
And then our brake pads is going to be, I guess, continuously increasing over the time. But we've got brake pads spec to, I can check again. I believe it was, I'm not entirely sure if I have the number, but our brake pads are spec to withstand it. If you want me, I can check that out.
Hold on. As long as you already.
Yeah, we did run the calculations.
Because those are aluminum rails, right?
Yes.
So,
And is that the point at which you would worry about the air bearings keeping the vehicle above the rail during the hard braking? In other words, when you have the pod shifting, is that something you're calculating?
Yeah, we're doing like basically just the vehicle tipping calculations with the torque from that braking. And what we can do is during our descent, or basically during our deceleration phase, as we apply those brakes, we're going to increase the airflow in the very front of our pod. So that way we can actually, and with our sensors, we can actually calibrate that as we're going, doing continuous monitoring to alter the height of the air ring, so we're still not turning.
But if you have a catastrophic failure condition in power, your sensors aren't going to work.
Yeah. Sorry. So by that I didn't mean we would be having that be our only mechanism. Like no testing, we don't need that. So we're gonna have a default increase in mass flow, and that's just gonna be default no matter what. If our sensors stop working, that flow is still going to be there. And then depending on what our sensors are saying, as we go, we can alter that flow slightly. But we already have a plan, to increase that pressure by.
So will one of the tanks be always reserved for braking? Is that how it goes? Because if you run out of air, your brakes aren't going to work either.
Yeah, that's a very good point. We will. I mean, that's definitely something to think about. I'm not entirely sure if it would be possible for us to run out of air without us realizing, because these will be continued. The tanks will be monitored, and if there is a power shutdown, we'll be braking immediately anyways. So.
Right, but in any, no matter how it goes, it should be one tank. I mean, as a redundant, there should be one tank that's reserved, because even if you have extra air, if all the tanks are functional, you never know. You might all of a sudden not have. So you want to at least have one air tank that clearly is
always going to be
and huge safety margin that you can always be able to brake.
And did you say you're doing a 3 to 4 millimeter gap?
3 millimeter.
Oh, okay.
Yeah, because the track, it has a maximum deflection of 1 millimeter, and they expect us to have a factor of safety on that. So as to not create, well, first of all, not to hit, and also not to cause major deflections in the airflow, we're rising it up to 3 millimeters.
And so you calculated at over a ton, which is what you're saying your pod's going to weigh. You can actually maintain that big a gap and still have air.
We're trying to.
No, but what does the calculation says?
The calculation.
Theoretical stuff, can you have a gap?
Yes, you can. It just requires a lot of mass flow, but we're trying to figure out the correct amount of that mass flow. and that's why we're double checking our calculations and everything. But we're getting relatively reasonable numbers right now.
And
Like
before your presentation, you were using some modified form of compressible Bernoulli
Yeah.
equation. Are you still doing that, or are you moving on to
we're
something else?
moving on to other things to look at them. So that one was a heavy approximation, but we're trying to do something much more accurate.
Good.
So that once we actually start doing the tests, that we don't have to modify things too much. So
Oh, and you do have contact breaks too, right?
We do.
When does the contact break come into play?
The contact break initiates at 30 miles per hour.
Oh, at 30
And
miles an
that's
hour. Okay.
actually when the maximum heating occurs from that.
Oh, okay. So the contact breaks will only when you're at 30 miles an hour.
Exactly.
And so you're then totally reliant on the eddy current breaks down to there? Or to that?
So technically, so ideally, in an ideal situation, our eddy current brakes will slow us down from 200 down to 30. But our friction brakes are spec'd to slow us down from that as well. So
From what? From 200?
200 down to 0.
Oh, okay.
So basically, we've got two systems. In case there's eddy current brake failure, we can rely on our friction brakes. In case, I mean, to be perfectly honest, I guess the only way the friction brakes could fail is if kind of the pneumatics themselves like fell out or something. But even if that happens, we're going to be down to at the very least 30, and we can still land on our wheels and go down from there with our eddy currents.
Now that you thought of it, Murphy's going to make sure that
Sure.
actually should have thought of it. But so but you're doing all your calculations for just this pod in the competition specs.
Yes, right now.
Have you taken a look at when it's the actual scalable to 700? Because right now all your calculations from 200.
Yes.
So what happened from 700?
Yeah, good question. So from 700, basically in a commercial scale Hyperloop, the friction brakes are not going to definitely, like 100%, there's no chance the friction brakes are going to slow us down from 700 miles per hour down to 0. But
Sure.
the good thing though is that in commercial scale Hyperloop, the acceleration deceleration mechanism is the normal non-emergency mechanism. Is going to need to fairly certain. The only way that, in my mind, is going to work is if we do use a linear induction motor to accelerate up to the 700 miles per hour and then do deceleration from there. So that's going to be normal case, which is kind of what you proposed in the white paper. And then in that case, the eddy current brakes are going to be a perfect emergency brake, right? So a contactless emergency brake down from 700 to a reasonable value where the pod can land and slow down using just a very, very minimal friction brake. And those calculations we've done as much as we can to verify that it works. Eddy current brakes haven't been tested at 700 miles per hour, and simulations go a little bit wonky at that speed. But it seems, based on experimental values, it seems like it's almost an asymptotic curve, basically, of braking as velocity increases. So it basically goes up and declines down to a fairly constant value at high speeds. So that's only been tested up to 300 miles per hour. But extrapolating to 7, it seems I'm fairly confident that they're going to work.
So Tyler, some of the viewers had a few questions regarding how we would be actuating friction brakes. Could you?
Yes.
You might want to get near to the.
Yep. Hello. So we will be using not springs but pneumatics for our friction brakes. We're going to have pneumatic cylinders that are coupled with pivots on either side so they don't shear under the friction force, and also obviously supported and attached to the chassis. So those, we've decided to use pneumatics for that, partially because we have our onboard air tanks. It makes it a pretty nice fail-safe approach. So in the case of any failures, we can open one of those valves to the air tanks and activate our pneumatics. So another question was our estimated spring force. So our pneumatic force, our direct normal force that we're going to be applying is, sorry, I don't have it in pounds. It's 16,300 newtons. And we spec for that, assuming we needed a deceleration of half a G, and then we added factor of safety of 2 onto that. So we basically used that combined with the coefficient of friction of our brake pads that were specified earlier. That's around 0.32. So we're going to be pneumatics. Sorry, so that's going to be the answer to that question. Next, pneumatics to apply the friction brakes. What pressure does this need? So we're using a series of 3 pneumatics on either side of the rail to apply the force for the friction brakes. And the pressure within each pneumatic is going to be 80 psi, and the amount of force the direct amount of normal force we're applying to the rail combined from both sides is going to be 16,000 newtons. Cool. What type of batteries are we using? Question for Mitch.
Okay, so the type of batteries, originally we were using a SpaceX, or Tesla type array, which got changed up fairly heavily since we dropped our compressor. Now we are still using a very similar array of CNCR, like Panasonic LiPo batteries. And they're going to be in a customized array that gives us the amp output and the voltage output that we need based on which subsystem that it's specifically powering. So I think that's pretty much it. I need to redo some of the calculations, but I think they're 3.3 volt at, what was it, like 1 amp? Not 1 amp each. Like 1.2 amps or something.
What are your power requirements?
So that's going to rely heavily on the eddy current brake, because that will be the most drawing system of everything. To 80, that was 15.
Yeah.
For braking and
Yeah. So the heaviest is going to be the eddy current because we're drawing, and everything else is going to be actuating just valves. So that's very, very minimal. And then
So you'll calculate your amp hour requirements.
based on the eddy current, and that's also why we're doing the custom array, is because those are going to suck a massive amount in a very short amount of time. So
And that's something that can tax the battery.
yeah.
Yeah, definitely.
So
We can test that.
yeah, that's the idea of the individual arrays that we're customly making, so that, because at our original power for the compressor, you were at like 500 kilowatts for the journey. I was like, whoa, you're getting into crazy territory. But for the new, it's a lot more reasonable, and we're hoping to space out the wear on the batteries by spacing out the like individual battery packs themselves into smaller arrays that can, as they go bad, just quickly get replaced by a new array.
So there's a lot of talk and obviously need for testing, these testings. In the budget that you've calculated, that takes into account building these testing jigs
for the
and the design of these jigs?
which number was that?
Well,
It would be
on any of them.
$23,000.
Just the budget that
We have
you
yeah. So within that budget, yeah, we did it.
you allocated for building jigs,
Yeah.
testing jigs.
Rich, there's a question regarding the overall pack voltage and amp hours, which
Pack voltage, that's going to depend on the subsystem that it's powering. For example, the computer systems will take a lot less of a voltage requirement than the eddy current brakes will, similar to the amp hours. I think overall, I had previously calculated it to be, I think it was 60 or 100 amp hours. I don't know. I can't pull that number off the top of my head right now. We've gone through a couple of design changes that have heavily changed that number.
so there's some questions about the electromagnet ECB power requirements and voltage. All right, so you can see the question.
Sure. All right, so a couple questions about the eddy current brake power requirements and coil configuration. Our power requirements are going to be around 15 kilowatts, I believe, for those. And the configuration, we plan to have configuration similar to the configuration used on Deutsche Bahn's eddy current brakes. So basically, it's a steel yoke with, an iron yoke with the coil wrapped around. Sorry, I'm not entirely sure. I'm fairly confident it's not on this computer, so I can't show it at the moment. But we're planning to get basically just a bipolar electromagnet for us, the amount of field reach out we can get, right? So the more field reach out we can get, since we can't put these electromagnets too close to the face of the I-beam, the better the field reach out, the better. And they're going to be coasting on either side of the I-beam with the face of the electromagnet faced against the I-beam, and then alternating poles. So north, south, and then south, north on the opposite side. So that way we're getting as much field flowing through the center of the I-beam as possible, and then inducing as much eddy currents as we can. Core elimination, I'll need to get back to you on that because we're still looking into that actually. Sort of. I mean, we're going to need to create some of it ourselves. So, all right. Let's see. How are we safely charging our battery packs? Mitch, you want to take that? So, can I have some computer? That's a question. Thanks. Okay. So, safely charging these packs, we will be creating a panel on the outside of our pod that will both have and what's it called? Nipples for the air canisters and plugs for each of the battery pack. These different battery packs will charge just with normal outlets and via I don't know how to put it in words. It's just they'll plug into a specific voltage and amp that is required for that specific or for that battery pack, and that way we will avoid charging the high battery or the heavy use or not heavy use. The higher voltage battery packs with the low voltage and the low voltage with the high. So pretty much it'll just be a panel with different sockets for each voltage level. There was a question.
So yeah, we apologize for not putting up a full pod assembly, and actually we do not have a completed full pod assembly. This is probably the closest thing we have, because we've recently switched to using Fusion 360 by Autodesk from SolidWorks. And throughout this time, we haven't quite finished assembling everything. So,
By the Fusion 360 from Autodesk.
yes.
Oh, but you converting it from SolidWorks.
We converted from SolidWorks to Autodesk, and a lot of this was redone from scratch in the past few days. So, this is as far as we got. All right. Cell balancing.
What is that?
That's where you can cell balancing.
Could you clarify that last cell balancing question? At this time, I would say I am unsure, and I will look into that further.
You were talking about safely charging. So on the subject of safety, are you required to or planning to or think you should have fire suppression?
In the battery or
Anywhere you think there's going to be a fire.
I can
So,
explain.
yeah.
His expertise. So the main areas, so the main areas of the pod that would cause a fire in our design. So first, let's start off with our design. So the only place that would really cause a fire is the batteries, and so those are isolated from the passenger cabin, and there's a double-layer wall between them. So in case there was a fire, it wouldn't get in. And plus, that area we're considering keeping it vacuum sealed, so it's impossible to have a fire. And so those are two things we're thinking about. In the actual full pod, there's more danger for fire from the compressor and from other elements, but in our case, it's just the batteries.
What is the pod made of?
So the pod is made out of.
So currently our pod is designed with a steel skeleton and aluminum paneling, currently a 32nd thick. And we have been in the talks with the carbon fiber sponsor and are considering changing our paneling to carbon fiber in order to reduce weight. However, that hasn't gone through yet, so we're sticking with aluminum, as we know how to manufacture aluminum versus carbon fiber. It's a little messy. If we were using an aluminum and steel design, none of the pod structure is actually highly flammable, so it's less of a concern. However, if we're switching to carbon fiber, then we would have to worry about the bonding actually burning.
Also, the air gap between the passenger cabin and the battery area. So there's a double wall with an air gap that also provides a ton of thermal insulation and would also protect against fire and explosion. So.
And you said that you're going to maintain the passenger compartment in some near vacuum state. Is that the idea?
No. That's the battery compartment.
The battery.
Yeah. So they're separated completely from the passenger cabin in terms of sealing.
So this is actually a recent design change. In the previous design, it was just an insulating wall that was placed around it and sealed with rubber. In this new design, we've actually separated the front and rear packages completely from the passenger compartment, such that we can pressurize them both separately and have the front and rear where the batteries are stored at a lower pressure, and have the passenger compartment at normal pressure.
And is the reason for lower pressure fire?
Fire, better maintenance.
There's actually also a benefit of keeping it at lower pressure in the case of a tank breaching, because when it breaches, it's going to release more air and increase the pressure there. And if we're increasing the pressure from a lower pressure, it's going to put less load on our overall system. Versus if we started from higher pressure, it would be higher.
Okay, if you're thinking about that argument, you can work on and have your plan for. From the fire perspective, vacuum is harder to maintain than pressurized with an inert gas.
Okay.
Nitrogen or carbon dioxide or something.
Okay.
There's an air bearing safety question.
What components have you? The bottom of the air. Okay, so there's a question on air bearings. So basically, yes. So this is the whole reason behind our safety factor of safety in terms of levitation. So as SpaceX has provided their specs, the track should not rise more than 1 millimeter above their standing position. So for that reason, we're going at 3 millimeters, and with proper calibration, they should never hit or even come close to hitting the metal. And so that's basically how we're preventing contact between the two surfaces.
If I may follow up on the fire question again, do I get it right that the passenger compartment you're assuming will not or will never experience a fire event?
So the passenger compartment, we have nothing flammable in there except so in our pod doesn't have lights, but the actual one would. But in our pod, there's nothing flammable in there.
No ignition sources, what you're saying.
Oh, no ignition source.
In the prototype pod we're building for SpaceX, there is no ignition source whatsoever.
Right.
Are we even putting the seat in?
Well, the seat material is still also being decided based on whether we get the carbon fiber sponsor or not. As of now, even the seat is not flammable. So
there's no fuel and no ignition source. However, in a scaled-up design, we have actually thought a little on this. There would always be the chance that someone's electronics misfunction, or someone lights a cigarette in there, or something happens. And in that case, we would need some kind of mister system in order to put that out. And keeping that in mind, however, we don't plan on extending on that in this design.
But you do want to think about it, because one of the things you took is scalability.
That's
right.
So you have to solve the big problem.
Yeah.
Not build it completely, but understand
Right.
how it goes.
we can make recommendations for that.
Right.
There are weight implications.
So the other on the battery balancing, you might want to talk to the solar car people. They've solved that problem. They talk about that all the time. It's the balancing, because they have multiple battery cells and they're constantly charging this up. But they have the balancing figured out.
And did you say you have all pneumatics, or everything is air? There are no hydraulics.
So we've designed our systems only using pneumatic systems because we knew we would have to carry air for the air bearings. So we've actually avoided using hydraulics for that reason. And that was just to not have to carry fluid, and also because pneumatics actually work as a better failsafe than hydraulics, since we can just have a valve default open, versus for hydraulic we would actually have to pump the fluid, which would require battery power. There was a question regarding how we would manufacture the conical and cylindrical pieces, with just conical pieces that are in our chassis. And we plan to actually outsource most of our manufacturing of paneling. We are in the talks with a few manufacturers right now who would be able to roll the cylindrical and conical pieces quite easily. How do you account for the possibility of acceleration if you're not performing your mass situation? So Tyler, this question is about essentially braking.
Right.
Braking tipping. No, it's
It's stay with the pitch moment. All right, yeah. So question about the accelerator interface not being perfectly aligned with our center of mass. So I assume that means kind of for the possibility that. Okay, yeah. So and I'm not entirely sure specifically what case you're talking about there, but in general, for load cases like that, we're going to be using basically, for example, if there's a freak accident where the SpaceX pusher is pushing at an angle that our pod is not designed to handle, first of all, we'll be counteracting that as much as we can with our air bearings and with our laser distance sensors on the front of our pod. Which will be basically calibrated to keep us at our normal levitation height. And if there is something wrong there, that'll be sending responses back to our control computer, and from there we can deactivate the pusher and slow down. I think, please phrase the question again if I didn't answer it, but sorry. Hopefully that answered your question. Let's see. Control system, overall system. All right. Yeah, here you can just clarify that.
I'll answer the control topology. We had it up earlier, but I can switch back over from our FEA model to the control system. Just give me a sec to figure out Google Hangouts. And it's not letting me switch over. But okay, I'll keep trying, but I can just explain it for now. So we're centered around like a canvas, and it I can't. It's hard to explain. Yeah, I might have lost connection on my computer. There we go. Okay, one sec. Give me a sec to get it. Okay. So here we go. Here's our system. So we're centered around the canvas, and we have these 5 computer systems. Levitation will be split into 2 eventually. So it's like there's a 10-second delay. Okay. So yeah. So coming up now, or came up a couple minutes ago, but we're centered around the canvas, and we have 5 separate computer systems and a total of 6 CPUs or 6 embedded systems. Levitation is going to be split into 2, with one computer system being air bearings and the other computer system focused on the brakes. Other systems are the air tanks and batteries, which will monitor like voltage output, amp output, make sure we're not running low on air and that all of our pressures are nominal at the tank side. There will be a double check on that at the air bearing side for levitation and height. Interior monitors air composition and any changes in the passenger compartment to make sure that all the passengers are safe and going well on the journey. Communications and navigation. So navigation is where we are in the tube, how fast we're going, what we're doing. Oh, okay. So are you talking sensor-wise or just how the computers talk to each other? Sensor-wise, okay. So, okay, so basically I'm gonna go with the sensor system. So at our air bearings, there will be distance sensors facing the ground. These will be a pretty closed loop where you're either too high or too low. And this is gonna be semi-passive because if we go too low, the air bearing should automatically correct based on the pressure. And if we're too high, they will sink back down to the correct level. However, we do still have to monitor this and be able to adjust the valve in the case that one of our tanks is bad and we have to open up the valve further in order to reach that nominal pressure. Over to the air tanks and batteries, it's just a simple passive loop of is the temperature good? Are our batteries outputting at the correct values? That there's not too much to control over there. There will be emergency shutoffs for velocity gap height. So gap height I addressed earlier with the air bearing. Forward velocity will be we have our initial acceleration phase, which we'll monitor with gyroscopes and the laser vision sensor at the top up here, which monitors the strips. Generating errors, signals for that.
Thanks for your feedback.
Thank you for the feedback. Yeah.
Yes, pass it on.
Yeah. Oh yeah.
What's happening?
Also have the suspension. Oh, okay. Okay, I see a question from you. Okay. So I see there's a question about the lateral air bearings, how we've determined the model of the lateral loading. We are still looking into that, and we are also doing tests with that in motion. These lateral air bearings are all rated for over 700 newtons of force though, so that's how much they can generate if they get within 5 microns of the I-beam. Ideally, they would not get to that close. So the vast majority of our testing is going to be done soon with the lateral air bearings once we actually have them here. And yeah, it's mainly a question of how straight the track is. In a perfectly straight track, they would be putting no force on, but no track is perfect. So.
The point you mentioned earlier about the flux. It is true that too much air bearing flux causes our pod to bounce. However, we'd just like to point out that there is a suspension system in place between the base package and the actual compartment where the passengers ride, which would, and this is designed for sake of scalability, which would prevent vibrations from being felt by the passengers.
I gotta take off for a 5 o'clock thing.
Could you describe the testing rig? Ben, could you specify which testing rig for
air bearings?
Yeah.
Okay, so yes, as of now, we're currently designing smaller air bearings that are 4x4. And how we're gonna do this initially is that we're gonna place masses on these and send them in motion and see how increasing the mass increases the airflow required. And then we're gonna put these in motion and see how the speed increases, how the acceleration and speed affect the mass flow and the air bearing height. And after we get these and we're able to scale up this data and extrapolate it, we'll be able to put this on the actual pod and test it on there. The lateral air bearings will be tested on an I-beam, which they will just be propelled across, and we'll measure the forces felt on them.
Yeah, sure. Yeah, sure. So for testing rigs on the shoot, what are we talking about? Oh yeah, we're talking about electromagnets. Yeah, so for electromagnet testing, we'll just be using rotational test rigs, because we don't exactly want to build an I-beam and kind of chuck our array across it. So we'll just be using a rotational test, spinning aluminum disc with the same thickness as the I-beam thickness, and we'll be using that for both heating tests and then also for brake force tests that we can kind of back up with some of our theoretical things we've been working on in ANSYS and COMSOL. Let's see, how does the air brake work? So the brake, it's Brandon, it's not an air brake, it's a pneumatically powered brake. So basically there are 3 pneumatics positioned on either side of the I-beam, and basically these will be pushing brake pads into the center of the I-beam and basically centering us on the I-beam and slowing us down with that friction. And also ideally that's not going to be used at top speed. That friction brake is only going to be used in the last 30 miles per hour range. And then how are you managing heat generation in the oh yeah, thanks Ben. And then Darian, how are you managing heat generation in the disk of the test rig? Yeah, so it's not exactly something we'll be managing, it's more something we'll just be measuring. Is that the question? How are we measuring it?
Yeah, I think one of the things, which is the thought that I had too, when you build these tubes, you have to be careful that you don't artificially, because with the disc, you might be able to get more heat dissipation out of it than it is on the actual track. So your measurement of the heat might not be accurate reflective of the track. So you want to be careful of that in the jig. So you might think that the brick's working and you're not getting hot enough, or it's like, oh, okay, yeah, this is good. Our calculation says 150, and then your jig test shows that you're at 148, and you go, oh, okay. But then all of a sudden you don't realize that your disc brake might be dissipating too much heat on its own. Then it's not an accurate reflection.
Yeah, that's
try to test. That's the stuff you've got to be careful.
Yeah, that's definitely a really good point. Specifically,
trying to say is
Depends how you make the disc.
specifically on the disc, compared to an I-beam, the difference is with a disc we're only using, basically this disc is the only thing that's going to be heated as we apply our brakes. Whereas the I-beam, you have this huge stretch of I-beam, and only the sections that are getting heated, you're passing them by and you're no longer heating them afterwards. So for that specific test, I don't think that's going to be an issue, but definitely on other tests, that's something we should make sure we don't introduce anything into. If all airlines are cut, how are we actuating the friction brakes? Yeah, that's definitely a good point. If all airlines are cut, technically we won't be able to actuate our friction brakes.
I think one of the things that you might want to consider in all of these systems is, okay, even in the pod, you have to sort of think of it, because there's a lot here that you intermix systems with being passive, but yet you have sensors and control systems that's going through. You have to consider, a catastrophic failure, which is all of these things. And real systems that are critical like this, they're redundant, right? They're a redundant system that comes through. So it is valid, and you have to take a risk factor to see what are your odds that, yes, all lines can cut, and it can happen. It can happen. An airline crashed before just because the failure was on the tail section. It was just that one odd case where the redundancy systems were also hit, and boom. So so we have to consider it.
Then, I guess to expand on Tyler's answer, if all of our airlines are cut, it's true that we would not be able to actually friction brakes. However, this is why we also have any kind of brakes. In the case that our airlines are cut and our batteries aren't failed, we will still get the
And then from there we can deactivate our air bearings and land on wheels, which will slow us down by friction for the last bit. And then another, let's see, another question. Oh yeah. So, and then another thing is we're planning on having a separate tank designated specifically for the air brakes. So again, factors of safety and redundancy on that. So hopefully these will be, sorry, correct me if it's already defined. Okay, yeah, Duncan, good point on that. Our one concern with that is, so I know there are a lot of air actuators that are going to be, when powered, they pull back. The only issue with that is that the spring force that you're going to generate from the internal springs on those, we've calculated that those aren't going to be enough to slow our pod down. So yeah, very good point. So basically our kind of reply to that is that we decided to use the automatic default open valve from our air tanks to our pneumatics. So that way, if we lose power, we can still activate them. You're right. If we lose all of our air tanks, then we will not be able to use those. We will switch to other forms of braking.
I believe his understanding was that we were using springs that were pinned by actuators somehow, and then we would essentially retract our actuators and allow the springs to fire. And in this case, if we had an auto retract, even if we ran out of air, we would be fine.
True.
So this will allow us to use a fully mechanical system as a fail-safe in case of both electrical and air. So we'll look into it.
Yeah, we'll definitely look into it. From what we've gotten so far, we haven't been able to find springs that are going to be strong enough and basically will fit into a design that's actually going to be able to slow us down mechanically. But we'll definitely keep looking into it.
The other thing with, like, for instance, you said default valves just normally be open, which means that the whole operation has to be closed. Your power calculation includes that, right?
Yes.
Okay. Because otherwise, right.
Yeah, yeah.
have enough reserve power also.
That would, yeah.
Safety will open. But you don't get it safe, but you don't want that.
Yeah, just in case. Yeah. All right. Let's see. Are there any other questions coming up?
So I guess we didn't quite finish testing these, did we? Or is there another testing?
No, you talked about his. Do you have testing?
Yeah, my testing rate. So for testing the actual chassis of the pod, we plan to actually pressurize the inside to just under 2 atm. Rather than putting in a vacuum with a pressurized core, we're just going to overpressurize the compartment that would be normally pressurized. And that's simply because we don't have access to a vacuum that large.
Cool. Great. Looks like there are no more questions. Please feel free to ask any more that you may have. And yeah, I guess any questions from the room?
Talk about cost and schedule at all?
Oh, we hadn't been planning on it, but for you guys, yeah, we definitely can go ahead with that.
So, any questions that are reply. Thank you guys so much for watching us today and providing feedback.
I just want to make a few comments. Oh, it's okay. I mean, you're gonna get all these questions, safety things, and things like that, and you have to consider all of them, right? Especially since you're toting scalability, so you have to go through the exercise and make sure that that these are addressed. And I think from your diagrams and everything else on the surface, it wasn't mentioned that you will have redundant systems, right? In one way, these things are gonna be safe or fail safe is you have to have redundant systems. And all that does is extend the odds, right? The chances of everything failing. It's impossible to have everything just totally not, fail safe. I mean, so you just have to make sure that now and then that's where the budget that comes in. If you didn't initially thought about redundant systems, you might not have enough budget to build redundant systems.
Oh yeah,
right.
Sorry.
Yeah. But again, there's not going to be any. I don't think, right? They're not going to have passengers on the pod or anything like that. So yeah, but you still have to consider them. But because again, you're coding scalability, you want to make sure that these are all addressed for the scalable ones.
Yeah, definitely. Yeah, we do. Yeah, our budget does include all of the redundant systems. For this specific presentation, we didn't really stress we have all these redundant systems because we were trying to just do like an update on our design budget.
Yeah.
So yeah, we did include that in our budget.
So again, thanks for watching. We answered a few questions in the chat just now. So yeah, leave any questions you guys have, and thank you.
Thank you.
Thank you, guys.